tonight marks our 10th event of the series. We've heard from writers, historians, geologists, artists, and activists, all showing us different ways that we can approach learning about and from the world's complex water systems and the ways that people interact with them. Last week's talk by Dolly Jorgensen emphasized the relationship between technology and nature. And before that, Giacomo Parinello's demonstrated the deep ties between urbanism and the development of large-scale water management infrastructure. Tonight's speaker will tie these 2 points together, speaking with us about what he calls Water 4.0, or the fourth water revolution. Tonight's guest, David Sedlak, is a professor of mineral engineering and the co-director of the Berkeley Water Center. His research fields include environmental chemistry, water recycling, natural treatment systems, and, as we will hear tonight, the reinvention of urban water systems. Just as we rarely stop to think where away is when we throw things away, we also live in a society that has the apparent luxury of ignorance of where our water comes from and where our waste goes on a daily basis. Yet, as we've seen all semester, we are no longer able to ignore issues concerning access to and availability of clean, fresh water. As Sharon Day pointed out, the decisions that Minnesotans and Ohioans make about how we treat our rivers affect the people in Louisiana. And as Sandra Postel and Ellen Wohl both observed, we're rapidly losing access to healthy rivers. So as we wind up the SNC over the next few weeks, our speakers will be challenging us to keep our eyes on both the past and the future, to learn from the successes and failures of past decisions about water management, and to closely examine how our actions today will ripple into the future of human health and water sustainability. Therefore, I'm delighted to be able to welcome David to campus today, since his most recent work is on how deeper knowledge of past transformations of water infrastructure can guide us as we work to innovate a new approach to water management. So I'd like you to help me welcome David Sedlak.
Thank you, Ellen. Thank you, everyone, for coming out, especially those of you who don't have to be here because you didn't sign up for credit, so I always appreciate that. If you've had a chance to read Water 4.0 or skim parts of it or see a talk that I'd given in the past, you might have seen that Water 4.0 talks about the 3 revolutions in urban water that have already come. And it posits that there is a 4th revolution on the way. Tonight, I want to tell you about the 4th revolution that's already here. I want to talk about the way in which parts of the country are already moving towards a new form of providing cities with water. And I hope that in seeing the way in which this revolution's unfolding, you can gain insight into the way we might go about spreading this revolution to other places and solving other problems. And so in order to do this, I need to back up a little bit and I need to briefly talk about the first 3 revolutions in urban water, and they take up a fair amount of Water 4.0, and I'm just going to review them briefly to give you a reason to read the book. And then I want to talk about some of the things that I think are driving us towards this 4th revolution in urban water. And after I show you the drivers, I want to come to a place that's already recognized the need to build a new form of water supply and water treatment and water disposal and recycling for cities. And by looking at that system, maybe we'll learn how this revolution spreads in the future. So let me start, and let me start here with Water 1.0. And if this will, I guess I'll just do it this way. There. Water 1.0. So in the book, I call it 1.0, 2.0, 3.0, and 4.0. It's kind of like computer operating systems, you know, like you have a computer operating system and someone makes a small improvement to it, so you give it a number after the decimal point. So 1.1 becomes 1.2, and then it becomes 1.3, and then someone says, hold on, this doesn't work well anymore. Let's come up with something completely different, and you give it a number 2.0. And you go from there. And so what I tell my kids is like Water 4.0 is just like Windows 8 going to Windows 9, except this works. So what you can, I'm a Mac user, and we struggle with the computer tonight, so I can say bad things, but it's actually my computer that made the trouble. So in the book, I call the Romans and their way of providing water for cities Water 1.0. And it's because the Romans took ideas that had been floating around in the ancient world, and they created a system. They took elements that other people had come up with that they'd used to supply water into cities, and they systemized it, and they made it possible for a city of 1 million people to provide about 100 gallons per person per day of water. And that's pretty amazing when you think about it. That's like contemporary water use. That's not just the amount of water you need for cooking and bathing and, an occasional cleaning the house. That's like what we use in our house today. And if you think about how much water we all use, here are the Romans 2,500 years ago providing everyone in the city with that amount of water. And so this figure here shows you a map of Rome from the height of the empire, and this is the full extent of the Roman aqueducts. And so you can see those aqueducts brought water from a distance of 50 or 60 miles away into the city, a series of different aqueducts built at different times. And the water came into the city, and it was used for more things than just drinking. There were fountains in central squares. There were ways that people could access that water. The water was used for holding mock naval battles. They were used for the famous Roman baths. They were used all over the city to make the city not only a place that people could live, but a place that was pleasant to live. And when they were done with that water, the water flowed into the street. And the water went to the nearest low point in the street, which in the early days was a ditch. And over time, those ditches traversed all around the city, and the ditches got covered up because they were inconvenient to have ditches full of flowing water running through the center of the city. And so the Romans not only gave us aqueducts and imported water, they gave us sewers. And so the cloaca of Rome are also almost as big an accomplishment as the aqueducts that brought water into Rome. And when we think about why the Romans went and created a system like this, the first thing we recognize is that when you have a city with close to 1 million people, you can't get by on just the local water resources. You quickly run out, you quickly exhaust the groundwater. And if you're not located on the shores of a great big freshwater body, like one of the Great Lakes, you overwhelm the capacity of the rivers to provide you with water. And so the Romans did this in part because there was no other way to support a city of 1 million people than to have an imported water supply. But I also wonder if there we go. I also wonder if the Romans did this a little bit to show off. If you think about what the Romans did in their capital, these were the richest kids in the ancient world. And like the nouveau riche that they were, they needed to show their neighbors how much stuff they had. And they showed it by building great buildings and great monuments. And in some ways, the aqueducts and this flowing, inexpensive, inexhaustible source of water in the city was proof of Rome's power and the power of the empire. So fast forward, I'm going to skip all the medieval history, sorry, Ellen, through the antiquities and the period after the fall of Rome when cities were a lot smaller. And when cities became smaller, people didn't need to take the steps that the Romans did of bringing imported water into city. That is, you could get by with a well and a bucket. You could take your bucket down to the nearest river and draw water, or you could take water out of a well. And so it wasn't until the second half of the 19th century, when the Industrial Revolution came, that cities started to grow to the same size as they were during the Roman Empire. And so starting the second half of the 19th century, you had London and then Paris growing to populations greater than 1 million people and exhausting their local supplies of water. And when they exhausted those local supplies of water, they took a page out of the Romans' playbook and they started building their own version of Water 1.0. Gravity-fed imported water system through aqueducts, sewers to drain the water out of the city, and then disposing of the water in the nearest water body. And in North America, we did something very similar. These figures here show you the amazing gravity-fed system that provides New York City with its water. So before the New York City's Croton and Catskills watershed systems were brought into the city as a source of drinking water, people in New York were struggling to find water. They were drinking anything they could find. They were fighting over water, and they weren't consuming a lot of water. But when the people of New York made the investment in an imported water system, suddenly water was plentiful and water was something that was widely used. But if you look at the heart of that New York City water supply system, it looks like the Romans' version of Water 1.0, just bigger. So instead of 1 million people, you have close to 10 million people in New York. And instead of bringing the water in from 50 or 60 miles, you're maybe bringing it in from 150 miles. So it's the similar idea, just in a different time period. And if you go over to the other side of the screen, you see the Colorado River system, where in the early part of the 20th century, we came up with a way to bring water into Southern California and into Las Vegas and into Arizona to make it possible to live in Phoenix and Tucson and to live in San Diego. And all of this was made possible by a gravity-fed system that started in the Rocky Mountains and brought water down to the coast. And there you're talking about a factor of 10 bigger than the Romans. And you're also using that water for irrigation and creating farming in a desert. And so these are some pretty amazing accomplishments that were enabled by a pretty ancient technology. There was one difference, though, between the version of Water 1.0 that was built in the 19th and 20th century and the version that the Romans had. And that difference laid the seeds for the next revolution in urban water. You see, when the people of London or Paris or New York built their gravity-fed water systems, they had something that the Romans didn't have. They had the steam engine, and they had the water wheel, and they had more modern materials. And with these innovations, you didn't have to rely on just delivering the water to a fountain in the middle of a plaza and having everyone come with a bucket or a jar to take water up to their house. You could pressurize that water and send it all around the city and into people's homes. And that was like just the most amazing improvement in quality of life for people, because now instead of spending all your time hauling water up to your house and using it sparingly because it was heavy to carry around, you had more water than you knew what to do with in your house. And one of the first things that people did when they had this water flowing into their house was to give up one of their closets. Took a coat closet, they took a closet where they put their garments that they didn't wear very often, and they repurposed it by putting a toilet in it. So if you've ever heard the term water closet, think about where it comes from. Suddenly you have a closet and it's got water in it. And it's got water in it, so you have a toilet in it. And you have a toilet in it, so you don't have to have a chamber pot in the house, or you don't have to go out to a cold, stinky outhouse in the middle of the night. So that's a really wonderful improvement in your quality of life. But unfortunately, that convenience of putting your wastes into a toilet and diluting it with lots of water caused the next problem, because the only logical place to put this cocktail of human waste and tons of water was into the sewer. And before that, human waste was going into a cesspool, or it was going into a pile behind a house, and it was being taken out and put into the farm as a source of nitrogen and phosphorus fertilizer. But now it was being put into the nearest river and being sent downstream. And if you lived downstream of a big city, you were drinking the waste of the city upstream from you, and that's what caused the problem that led to the invention of the second revolution in urban water. So what we started to see in the late 19th century and the early 20th century were outbreaks of waterborne diseases, like the cholera epidemic that hit London and parts of Europe in the latter part of the 19th century, or this example, which I talk about in Water 4.0, of the cities of Lowell and Lawrence on the Merrimack River in Massachusetts. And I chose the cities of Lowell and Lawrence as the example for a couple of reasons. The first example is that Lawrence, like many places, when they started having problems with waterborne diseases that arose from having sewage contamination in the water supply, many cities just found a new source of water. They brought an imported water supply from a pristine source and they stopped drinking the polluted river water. But the poor folks in Lawrence didn't have an option. There wasn't an easy way to import water or to dig more groundwater wells, so they were stuck with the Merrimack River. And the people in Lowell weren't about to stop using their toilets and putting the water into their waste into the river. And so you had these incredible outbreaks of typhoid fever. And so what happened at that point was that in desperation, they needed to find a way to drink sewage-contaminated water. And these desperate people did what desperate people do all the time. They put their faith in engineers and technology. And specifically, the engineers they put their faith in were a team of engineers from Massachusetts Institute of Technology, MIT's Lawrence Experimental Station. And these engineers from the Lawrence Experimental Station took some ideas that had been floating around in different bits and pieces in the previous decades and created Water 2.0. And Water 2.0 is drinking water treatment. It's the way in which we can take sewage-contaminated water and drink it without getting typhoid fever, without getting cholera. And it's truly a miracle in terms of its simplicity and its reliability. Basically, the idea that the first drinking water treatment plants embraced was the slow sand filter. That is, if you pass water over a column of sand and you let that sand develop, what happens over time is that microbes grow on the surface of the sand grains. And those microbes secrete a slimy coating called a biofilm. And that biofilm acts as a glue and traps all the toxic microbes that can give people waterborne diseases. And so the sand filter and its microbial community was capable of removing typhoid fever bacteria and removing the organisms that cause cholera and many other diseases from the water. And these fellows here, Albert Hazen and William Sedgwick, MIT professors, really get a lot of credit for developing this system of Water 2.0. Now, about 10 years after slow sand filters were discovered and improved upon, people found out that they could also add chlorine to drinking water. And that chlorine disinfection step could act as like a second barrier. And this 1-2 punch of filtration and chlorination could really make it safe to drink the sewage-contaminated water. And within a period of about 10 or 20 years, people like Abel Wohlman from Johns Hopkins University had popularized this technology and spread it around the country. So in a period of from about 1900 to 1920, you went from a time when people were getting sick from drinking their city water supply to a time when it was safe to drink those water supplies because they'd embraced this revolution in water technology. And when you look back on the 20th century, you can see statistics from public health experts that show the average lifespan of Americans increased by somewhere around 15 years due primarily to safe drinking water. So it wasn't just typhoid fever and cholera that was prevented. There are a variety of waterborne diseases that people didn't even realize were waterborne diseases that were killing people and affecting their quality of life. And this revolution, Water 2.0, made it all possible. So there's the first two revolutions in urban water. Now, the thing that we weren't doing at that time, you might have noticed I said that, was we weren't treating the sewage that was coming out of all these sewers. So we had treatment on the front end, and engineers argued and argued about whether it made sense to treat the sewage to avoid putting these waterborne microbes into the environment. But they'd concluded, you know what, it was just more efficient to let dilution do its thing and to let the contaminants and the microbes disappear in the river and only treat the water you're going to drink than to bother trying to treat all that sewage. But there were some people who had a different opinion. There were people who thought it didn't make sense to put human waste into rivers and pollute those rivers. And they developed a technology which I'll call Water 3.0. It's the activated sludge treatment plant. There's a second kind of treatment plant called a trickling filter that uses the same general ideas, and it was also popular. But this activated sludge treatment plant is the treatment technology that most of us have treating our sewage today. So I don't know what you have here in this part of Ohio, but I would hazard to guess that you probably have an activated sludge treatment plant treating your sewage. And this technology was developed in the first 20 years of the 20th century by people like Gilbert Fowler at the University of Manchester. They basically recognized that you could use microbes, and those microbes could break down the organic matter and remove all the nasty things in sewage and turn that nasty sewage coming into a sewage treatment plant into relatively clean water. So we had this technology developed in the 1920s that made it possible to treat sewage and prevent a lot of the problems that sewage discharges were causing, but most people just didn't think it was economically a good idea. And so you have this period from the 1920s through the Depression and through the Second World War and even after the Second World War, when the quality of surface waters in North America and Europe and many other places became worse and worse as population density increased and increased. And if you look back at the history of this time period, you'll see people complaining, the Great Lakes have too much algae, the Great Lakes are dying, there are fish kills. Oh, we can't walk by the Potomac River because it's just so nasty. The smell of hydrogen sulfide is disgusting. Oh, San Francisco Bay? No, you don't want to live near San Francisco Bay. The hydrogen sulfide coming out of the mud flats is enough to decay the paint on the side of your building. All of these things were happening, and people said, you know, someone should get together and fix this. Isn't it a shame that the lakes are dying? We should really do something about this. But no one could get together the political will to spend all of the money that was going to be needed to install modern sewage treatment plants in American cities. No one could do that until the Cuyahoga River caught on fire. And no one could do that until people became aware that bald eagles and ospreys were disappearing due to the effects of DDT, which is really kind of an irony, is that the catastrophes that led to the modern environmental movement had nothing to do with sewage disposal. But what happened is when the public decided that the quality of the environment had deteriorated to a point where it was no longer acceptable, we chose a shovel-ready solution. We knew that we had these sewage treatment plants and they could improve the quality of our surface waters. They wouldn't necessarily prevent rivers from catching on fire. They wouldn't necessarily bring back the bald eagles and the songbirds, but they would make it possible to go down to our rivers and to swim in them and to fish in them again. And so this figure, wrong direction. This figure here shows you the federal expenditures in billions of dollars from 1972 to about 1992 that the country spent on the Clean Water Act, mainly to build sewage treatment plants. And so after the public was galvanized to do something over a 20-year period, we spent something like $25 billion to upgrade our sewage treatment plant infrastructure. And anyone who has grandparents or parents around who had lived through seeing the Great Lakes in the 1970s would tell you they're greatly improved from what they once were. And that's largely due to this miracle of the third revolution in urban water, a technology that had been invented 50 years before, and it just took a perceived disaster to make it something that we wanted to spend money on. So here I am telling you that I think there's a fourth water revolution and there's a need for a fourth water revolution. And I have a pretty high bar to get over to convince you that it's worth spending the money to do it. Because for the second revolution in urban water, we had to have a body count. We had to have cholera victims and typhoid fever victims. And for the third revolution in urban water, we had to have rivers catching on fire. And we had to have birds disappearing. Why do I think it's time for a fourth revolution in urban water? Well, most of my remarks tonight are going to pertain to water supply. So I live in a part of the country where water supply is not secure. And many people in the United States have a water supply that's increasingly going to become insecure. You folks are lucky. You have a problem with too much water. So you have a different revolution to pursue. I want to show you tonight my revolution in urban water supply. And hopefully, when you try to solve the problems in your region of the country on having too much water, combined sewer overflows, pollution of surface waters, you can learn from this lesson. And so for me, the number one concern with respect to the future of our urban water supply in the long term is climate change. And I can say that because the science of climate change is showing us that the rainfall patterns are going to be changing. So this figure here, which comes from the 2013 IPCC report, which summarized the state of the science on climate change, tells the story that the wet places are getting wetter and the dry places are getting drier. So if you look at this figure, the axis here, or the colors, refer to the percent change in mean annual average precipitation for each degree centigrade of warming that's going to occur. So in other words, in the 21st century, the average temperature is going to increase by several degrees centigrade. And we have the power to decide how much that increase is going to be, but it's definitely increasing. And for each degree centigrade increase in temperature, some places are going to see 3 or 6 or 9 or 12% increases in precipitation. That's the blue. And some places are going to see decreases in precipitation by 3 or 6 or 9 or 12%. And so the areas that are brown and tan colored here are the places that are going to get drier in the 21st century. And if you look at this figure, you're going to see if you're in Australia, or if you're in the southern part of Africa, or if you're in much of South America, or the Mediterranean region, or the southern and western United States, parts of North America, you're going to see less rain, less water. If you're in the Great Lakes, more water. Sorry about that. But that's the problem with climate change. Some places are going to win and some places are going to lose. Now that's one thing that's going to decrease the amount of water available for cities in much of the world. But there's another thing that's going to decrease the amount of water available for cities in much of the world, and that's the change in precipitation from falling as snow to falling as rain. And so in the Rocky Mountains and in the Sierra Nevada mountains of California, much of our precipitation happens in the winter, and it happens in the form of snow. And that snow has this wonderful property of staying put. So it becomes like an in-place water storage system. Now, when it gets warmer, more and more of that snow is going to fall as rain, and if we want to use it, we better be able to trap it by expanding the size of our reservoirs. And that's going to be an expensive proposition, and that's not going to be an easy proposition politically. You can imagine with the fights that we have over removing dams now, the prospect of increasing the size of dams is going to be really politically contentious. I think we could probably do that in the Rocky Mountains and in California and parts of North America, but there are other parts of the world like Peru and India where people rely on glaciers as a source of water storage. And the predictions are that once those glaciers disappear, there's going to be severe water shortages in India and Peru and other places. So certainly climate change is more than just a change in rainfall patterns. Warming is going to decrease the availability of snow. And then the other thing that's going to happen, as you all know, is that when it's warmer, water evaporates more quickly. So more of that water that falls on the land is going to evaporate before it makes it to a reservoir. And people living in cities, when it gets warmer in a city, people use more water. They use more water because they want to maintain a lawn. They use more water because they want to grow crops. They use more water because water mitigates the urban heat island effect that occurs in cities. And so that's a second reason why climate change might be a real problem for water supplies in the future. So I wanted to kind of dwell on this topic of water availability for a little while and the effects of climate change to show you something about the current state that we're in, and then to help you see that this is a problem not just of Southern California or places in the American Southwest, but it's a global problem. So this figure comes from a paper that was published in the journal Science a couple years ago, and it shows kind of what you might call the water availability stress, or water stress index. So it's kind of the ratio of the amount of water that's used to the amount of water that's needed, and it's looking at two different things. Whether we have enough water for people, that's human water security threat, and so you can see if it's in red there, it's a high threat, or brown or red, and then you can see the biodiversity threat. If there's not enough water, if we're using too much water for the environment, that's in yellow or in red. And so the areas in red, like the Sahel in Africa and India and parts of China, are places where people are taking more water than the environment can handle. But when I see these kinds of figures, I feel like they don't tell the story about what's happening in cities. Because cities are 100 or 1,000 times more concentrated with respect to people, and they have this huge water demand. So I want to just show you examples of two cities that are currently struggling under water availability problems due partly to population growth and partially to climate change, places where I think it's going to get worse in the future. So this figure here shows you the main drinking water reservoir for the city of Sao Paulo, Brazil. So the Sao Paulo metropolitan area has about 20 million people. And when I snapped this figure off of the website for the city a few days ago, they were at 3% capacity of their reservoirs. And it was estimated that in the next week or two, Sao Paulo would run out of water. I looked at it today. The number blipped up a little because at great expense the city brought in water from another part of the state in Brazil. But Sao Paulo is essentially out of water. And they're out of water because they've been experiencing a drought of historic proportions, and they're out of water because the population of their megacity has been growing quite quickly, and they haven't been able to keep up with expanding their infrastructure. Another example, Perth, Australia. This figure here shows you the annual precipitation in Perth starting in the year 1900. So those blue lines there show you the average rainfall in Perth, and then the green and the yellow lines show you the long-term running average precipitation. And what this figure shows is that about 10 years ago, Perth's precipitation decreased by about 10 or 20% per year. Rather 10 or 20%, and the average stayed down. And based upon changes in the ocean circulation patterns that are attributable to climate change, the meteorologists and hydrologists in Perth don't expect that rainfall to ever come back. And so in response to the permanent decrease in rainfall, Perth has made a major shift to obtaining their water from seawater desalination plants. So you probably heard that, like, Saudi Arabia and these Arab oil emirates and Caribbean islands use seawater desalination for water because they don't have any other choice. Well, Perth, one of the biggest cities in Australia, now gets about half of their drinking water from seawater desalination. So this is a problem, obviously, that isn't going away and isn't localized just to Southern California. But I do want to spend some time talking about California tonight. So this map comes from a website called the Drought Monitor. And the Drought Monitor is a government NOAA forecasting tool that shows the state of drought in the United States. So as you might imagine, in all these kinds of graphs, red is bad. And this figure shows you some pretty dark red in California because we're in the middle of our worst drought in, I guess people say 80 or 100 years. And it hasn't really, I didn't think to bring a raincoat or umbrella with me because I just don't know what rain is anymore. And so this decrease in rain in California is not just limited to California. You see a very severe drought in Texas, especially in central Texas. And until last year, we had drought conditions in the Rocky Mountains. And if you recall back to that figure I showed you from the IPCC report about predictions for the future, this is the future we can expect for the southwest and southern part of the United States. The problem of a decrease in precipitation attributable to climate change is not our only problem we face. We face this problem of population growth and shifts in population in the United States. So this figure shows you the county-wide population of the United States and the way it's changed from 1970 to 2030. So demographers somehow have crystal balls. They know what's going to happen in 2030. These are their projections. So if you look at this crazy figure, you'll see that the irregular shapes are all of the counties in the United States. And the height of each of those counties is proportional to the number of people living in the county. So you can see New York City and Manhattan, really high bar because it's one of the most densely populated parts of the United States. And the areas shown in blue are areas that have been and will be losing population, and the areas shown in red and orange are the areas that are gaining population. So what do we learn from looking at the demographics of the United States? The people are moving to the south and the southwest. It's exactly where the water isn't and where it's not going to be in the future. So I took the liberty of putting the 20 largest metropolitan areas on this figure, and they're labeled here. And I labeled the ones in red that I thought were going to run into water security problems in the future, and the ones in blue as the areas that probably won't run out of water anytime soon. So if you think about all these areas in red where the population's growing at 1 or 2 or 3% per year, over a period of 20 or 30 years, we can expect 50% less water, 30 to 50% less water. So if you tell me that we can solve this problem of inadequate water supplies purely by conservation, I'll tell you that population growth is going to eat up our efficiency gains. So there are still lots of things we can do to make our water systems more efficient, but population growth is working against us. And so the way I see it, we have a period of about 20 or 30 years before our water stress morphs into a water crisis. You might think 20 or 30 years, that's a long time. you don't need to worry about this until it becomes a problem. But working in urban water infrastructure, an area where when you build something, it's supposed to last 50 or 100 years or 200 years, working in an area where the public isn't particularly engaged or informed, and looking at problems of national infrastructure during a time when the government seems to have lost an appetite for maintaining and improving infrastructure, you can see that we're going to have to pedal as hard as we can to head off this crisis. And so what I want to talk about tonight is how we're going to make that transition from Water 3.0, shown here, to the future of urban water systems. So this is Water 3.0, the system I told you about a little bit earlier. Water comes in on this side, imported water, water from different sources. It comes through a water treatment plant. That was Water 2.0, you might remember. It gets used in the city. Okay, that's a schematic of a city, but that's a city. And it comes into a wastewater treatment plant, Water 3.0, and it goes out into the environment. And depending on whether you have a combined sewer or a separate sewer, it may or may not, the runoff may or may not go through the sewage treatment plant. But this is a linear system. Water comes in on one side and goes out the other side. This is Water 4.0. This is the blueprint of the fourth generation of urban water systems. And what you can see here are a few changes. There are a few new boxes, and there are a few boxes who changed their names, and there are a few new kinds of arrows. So let me explain to you Water 4.0 kind of from a conceptual side, and then give you some examples about how Water 4.0 is being realized now in parts of the United States. So the first thing you see is that we no longer have sewage treatment plants or wastewater treatment plants. We have resource recovery facilities. And if you go down to your local sewage treatment plant, it might be called a resource recovery facility now, but that's just a matter of branding. In the future, these are truly going to be resource recovery facilities, and the resource they're going to be recovering is water. They might, they might collect some nutrients, they might get some energy, but water is the most valuable thing in sewage. And what they're going to do with this water is some of it they're going to send right back into the city. This is the concept of water recycling or water reuse. And you may have heard about non-potable water reuse, this idea that you could take water from the sewage treatment plant and use it in the power plant for cooling, or use it on the highway median for growing the grass, or send it to a golf course. But I'll tell you that the direction that we're most likely to go in is potable water reuse. We're going to take water from the sewage treatment plant and we're going to make it our drinking water supply. The other thing you'll see here is that there are two new boxes. There's one that's called managed surface water and one that's called a managed aquifer. And that's to emphasize the fact that natural systems are part of our urban water infrastructure. Right now, we don't acknowledge it. But when we put water into a river, that river is functioning just the same way a pipe does. And when we put water into a lake and take water out of that lake later, it's serving the same function as a reservoir. It's my contention that if we actively manage these systems, not only can they hold water and move water, they can purify water for us, and they can act and save us money and save us effort and make up for purer water by acting as part of the treatment system. The other thing, and they may act as such a good treatment system, they allow us to take this wastewater and bring it back into our city. That's another form of water recycling. So I told you that the title or subtitle of this talk was A View from the Other Side. And strangely enough, the other side of the revolution is called Los Angeles. And that's really strange to me because I live in San Francisco, and in San Francisco we make fun of people from Los Angeles as being superficial and being behind the times. We're the progressive ones. Well, in the case of urban water infrastructure, they're the progressive ones. And they're the progressive ones because they've had to be. Remember, Los Angeles is a city of over 10 million people that gets its water mainly from imported water sources. It gets water from that Colorado River system I showed you. It gets water from the eastern Sierra Nevada mountains, and it steals water from Northern California. That's at least what we say in Northern California. And so they see the writing on the wall. They know that there's going to be less water available to them in the future. And so they've started building the fourth revolution in urban water systems. And the illustration I want to show you to give you a sense of their current level of progress is this pie chart here. So this pie chart shows you the distribution of where the water comes from for Los Angeles in the year 2010 and in the year 2035. And what you'll see if you look at it is that in the year 2010, about half of the water comes from imported water. That's that Colorado River supply, that Eastern Sierra supply, that Northern California supply. And in the year 2035, that imported water is only going to make up about a third. And if we went to the year 2070 or something like that, it would be even less. So they're slowly weaning themselves from imported water. And the way that they're making up for that decrease in imported water is they're increasing the amount of recycled water that they use. They're engaging in something called capture and use. And they're doing something that in this figure is called WUE. That's water use efficiency. That's those efficiency improvements of low-flow shower heads and front-loading washing machines and smart irrigation controllers on houses that you may have heard about. So they know that these are going to continue to come, but they're not going to solve all their problems. I should mention parenthetically that groundwater pumping, you see here, it stays relatively the same. The city of Los Angeles is spending somewhere around $900 million in the next 10 years to make sure that it's possible to do that, because much of Los Angeles's groundwater supply is threatened by hazardous waste from the aerospace industry. So most of Los Angeles's drinking water supply, their groundwater supply in the San Fernando Valley, was located in the places where the large aircraft manufacturers were located during the Cold War, and they contaminated a lot of that groundwater aquifer. So it's going to cost close to $1 billion to clean up that groundwater and make it drinkable. But the city's willing to pay this because they have so few options for finding new sources of water. So what I want to do here is I want to spend some time examining the water recycling and the capture and use that's done in Los Angeles. So first of all, let me tell you about potable water reuse. How many of you think it's disgusting to drink sewer water? Willing to do it? You know, I have some in my bag here. You know, in Southern California, it's not considered such an unusual thing because there are cities in Southern California that have been drinking highly purified wastewater effluent for over 40 years. And the technology to turn sewage effluent into drinking water is shown in this figure. So if you ever heard of the technology of reverse osmosis, this way of removing salts and particles from water, that's the first step in this treatment process. And the second step is to take hydrogen peroxide, pretty much familiar with that, you can buy it at the pharmacy, and shine UV light at it. And when you do that, you make something called hydroxyl radical that breaks down. These are the free radicals that make us get old. These are the free radicals that make us stay alive. And so this treatment technology is part of the advanced water purification technologies that are used for these systems. And the first example where this was done was in a place called Water Factory 21 in Orange County, California, and this was a facility that was built in about 1976. So the people in Orange County were using their local groundwater, and they were pumping their groundwater too much. And if you've had a geology class, you may realize that water flows downhill. And when you pump groundwater too much, all the water nearby flows to that well that you're pumping from. And so if you pump the level of the water down below the level of the ocean, the seawater flows in. And so what they were starting to find is that the drinking water in Orange County was becoming salty from the effects of seawater. And so they took this strategy of building a line of wells about 3 miles inland and pumping fresh water into the wells to push the seawater back to sea. And the only source of fresh water that they could get was this highly purified wastewater effluent. And what they realized at the time, but maybe didn't publicize widely to the public, was that this water that they were injecting, not only was it flowing out to sea, but it was flowing back to the community and becoming part of their water supply. So this was the first potable water recycling project, the Water Factory 21. And that project was subjected to such public health scrutiny, and so many samples were analyzed, and so many health effect studies were conducted, and the regulators were pretty satisfied with the performance of the system. So about 6 years ago, they knocked down Water Factory 21 and they tripled its size. So today, somewhere around 50 million gallons per day of wastewater effluent in Orange County is recycled. Some of it goes back into those original seawater barrier wells, and some of it gets piped up to Anaheim and goes into a place called the Anaheim Lakes. It percolates through the lakes and becomes the local groundwater supply. And that idea of indirect potable reuse, or taking wastewater, putting it through an advanced treatment system and putting it into an aquifer, has spread to other parts of Southern California. So there are a handful of projects that use this exact same approach. In fact, people are so satisfied with that approach that the latest discussions have been, why do we need to take the water and put it back into an aquifer when we're done? Why can't we put it directly into a drinking water treatment plant or directly into the drinking water distribution pipes? And that certainly was what the city of San Diego and the citizens of San Diego said when the water utility in San Diego proposed to treat their wastewater and pump it back to the city's main reservoir. They said, why are you going to emit all those greenhouse gases pumping that water uphill just to put it in the reservoir when we can use it down here in the city? And so currently, the state of California is evaluating the potential for this idea of direct potable reuse. And we're trying to come up with ways that it might be regulated because we're a cautious state. We move slowly. We don't want to get out ahead of technology. But in Texas, they built 2 treatment plants to do this, and they've been doing it for close to a year. So in Midland and Odessa, Texas, there are treatment plants that are doing direct potable reuse. So if I had a crystal ball here, I'd say that this is likely to become something that becomes more common in the future. And I've been very interested in working with social scientists to understand whether the public will accept this new technology of potable water recycling and why some projects are embraced and celebrated by the community while other projects are rejected. So the Water Factory 21 moved smoothly, but maybe that snuck under the radar because they put it in 1976 before people thought a lot about their water. In the 1990s, there were a series of potable water recycling projects that failed because the communities rejected them. And yet there are other potable water recycling projects that succeed. And so working with social scientists, we've been studying the concept of legitimacy and how a new Sorry. I'll tell you about it, and maybe someone could help me fix the projector. Let's see. Give that a try. Oh, it popped out. That's an easy fix. No, it's on the other side. Let's see. No, I'm sorry. Maybe you can help Ellen or if someone's around. So with respect to legitimacy, the idea here is that technologies... Sorry, do you want me to stop? Or?
No, I'm sorry.
Okay.
I'm just going to try to do this.
That it's plugged in over here, or it thought it was plugged in over there. Whenever there's a new technology, people are a little suspicious of it. So in the early days of the bicycle, people thought this was a dangerous technology that people shouldn't use because it was unsafe. And in the early days of the airplane, it was viewed as an unsafe technology because a lot of people went out on airplanes and never came home. And so the airline industry underwent a process of legitimacy, or creating legitimacy for air travel as a transportation option. In other words, when you get on the airplane and you hear that announcement about safety, that's part of a plan to make sure that you recognize that the airplane company or the airline is focused on providing for your safety. And when you think about air travel, you don't think about the danger, you think about all the great places you're going to go and how it benefits you personally. And at this point, we're also familiar with the idea of getting on an airplane. We just take it for granted that this is a safe technology. And so when we think about whether or not water recycling will make this jump from being viewed as a potentially risky technology to being something that we generally accept, we see that the recognition by the public that this is something that's in their best interest is part of the picture. And we see that creating institutions that the public has confidence in with respect to assuring the safety is another piece of that legitimacy. And so I think there's interesting questions not only for scientists in this arena, now that's used for the Mac back there, not only for scientists in this arena, but also for people in the social sciences. So these are the 3 dimensions of legitimacy: pragmatic legitimacy, whether it serves the self-interest of the community; moral or normative legitimacy? Does it comply with a quality standard like in an airplane? Are they following the FAA regulations? And when there's a crash, do they bring in the National Transportation Safety Board and look for the black box? And then cognitive, does it mesh with your cultural experience? In other words, do you take it for granted that this is just something that people do? When we think about the idea of drinking water out of our toilet, that's the journey that this technology has to take before it's viewed as legitimate. And it's already done that in some places, and social scientists are teaching us how it's going to make that transition in other places. I also want to talk about another form of water reuse, potable water reuse, that most of us take for granted already. And that's this idea of de facto or unintentional water reuse. So this is a figure showing you the Trinity River in Texas. And the Trinity River is a convenient way of getting the wastewater from Dallas and Fort Worth into the main drinking water reservoir for Houston. In other words, the water in Lake Livingston, which is one of the main drinking water reservoirs for Houston, is about 50% wastewater effluent from Dallas and Fort Worth. And that water only makes a trip of about 2 weeks down a muddy river. It doesn't go through wetlands and reservoir and groundwater infiltration. It's not like you can say it's some other molecule. I can find human pharmaceuticals in there. I can find tracers of wastewater. I can see as a chemist that this is wastewater effluent. And that's a drinking water supply. So I told you about drinking wastewater effluent when it's put through reverse osmosis and ultraviolet light and peroxide. This is water that's been put through water 3.0 and put into a river and then put through water 2.0. So this is something that we do already, this idea of de facto water reuse. And I've been interested in this topic as part of my own research for about 15 years now, because I think this is a place where managed natural systems can improve water quality and make this form of unintentional reuse safer. And so the example and a place where I've done a lot of this research, again, is in Southern California, in Orange County and Riverside counties. It's in a place called the Inland Empire. So the Inland Empire, shown here, is a place where prior to about 1970, there were fewer than 1 million people. And today there's close to 4 million people in the greater Inland Empire area. And the main river that drains the Inland Empire and takes its water down to the ocean is called the Santa Ana River. And before all the people moved into the Inland Empire, the Santa Ana River was a typical California ephemeral stream. It flowed in the springtime when the snowmelt in the San Gabriel Mountains happened, and then it stopped flowing in the summertime. Well, today the Santa Ana River flows all year round, and for most of the year it's essentially all wastewater effluent from the Inland Empire. And the people in Orange County are really happy about that because that's an important part of their water supply. So remember I told you about how the Water Factory 21, when it was expanded, they sent their water to Anaheim, to the infiltration basins. Well, here's Anaheim, you can tell because you can see the Magic Kingdom. And in Anaheim, that water becomes, from the Santa Ana River, becomes the drinking water supply. So the water from the Santa Ana River during the summertime gets routed out of the main river water channel, and it goes into a series of infiltration beds. And as the water percolates through the sand, very much like water 2.0, the slow sand filters that were invented at the Lawrence Experimental Station, it undergoes a purification process. And upstream, there's a place called the Prado Wetlands that formed behind a flood control dam. And I have been interested in studying those Prado Wetlands now for about 15 years because I think that they could be used to purify the water and make it cleaner before it undergoes that infiltration process. So in the Prado Wetlands, or rather in the Prado Wetlands, in the late 1980s, they started to see that the concentrations of nitrate in the river were rising as the population grew in the Inland Empire. And nitrate is an important drinking water contaminant. If you have more than 10 milligrams per liter of nitrate in your drinking water, you can't serve it to people because of concerns about risks for young children. And so the city of Orange County, or the Orange County Water District, worked with a colleague of mine to try to make the wetlands the way to remove the nitrate from the water. And the way they did that was they built an area of densely packed vegetation. And as that vegetation would die and decay, the microbes would use nitrate as a terminal electron acceptor, and in that process they would convert the nitrate to nitrogen gas, a process known as denitrification. And I thought that was really a great thing. That was a wonderful example of how a natural system could be managed to improve water quality. Well, when I started doing research in the 1990s, in the late 1990s, I was interested in all the other stuff in sewage effluent that might make it to a drinking water supply. And in particular, I was interested in the human hormones, 17-beta estradiol and ethinyl estradiol. And the reason I was interested in these human hormones is that we had found that they were present in sewage effluent, and in places where sewage effluent wasn't diluted, they were feminizing the fish. That is, the male fish were showing characteristics of female fish because of their exposure to these potent estrogens. And so one of our first research projects sorry guys, there we go. In the Santa Ana River, or in the Prado wetlands, looked at using those vegetative wetlands to remove steroid hormones. And they didn't work very well for removing the steroid hormones because they had the wrong kind of microbes. And so then we conducted a research project in something that we called an open water unit process cell. This is something that we invented that could supplement the action of the plants in the wetland. It doesn't look much like a wetland at all. It's just a shallow pond where the water flows around these wooden boards here in and out of a basin. And the idea here was to use the sunlight that would shine down on the water to remove the chemicals, because many of these chemicals are susceptible to transformation reactions that are catalyzed by sunlight. And so we built this system intentionally to optimize. Don't beep at me. Well, let's see if that works again, huh? Well, at least we learned how to fix it, right? Well, we'll limp our way through this one way or another, huh? Oh, come on. There we go. So we used the effect of sunlight to break down these chemicals, and we found that this system worked pretty well. So here's some data here showing a series of human pharmaceuticals that we could measure in wastewater effluent from a treatment plant. So you can see, concentrations are pretty low. These are in nanograms per liter, so 10 to the minus 9th grams per liter. But these are a variety of human pharmaceuticals. So these are heart medications, atenolol, propranolol, and metoprolol, or antibiotics, trimethoprim and sulfamethoxazole, or an anti-epileptic drug, carbamazepine. And as we sampled in different parts of the wetland, many of these compounds disappeared. You can see them decaying away as the water flows through the wetland. Some of them didn't degrade. They weren't susceptible to degradation by sunlight. But many of them degraded, and degraded a lot more quickly than they ever did in the vegetative wetlands that we'd studied previously. And so the way we think about these systems is we think about them in terms of a footprint. That is, this figure here shows you the area needed, and this is on the exam, by the way, the area needed to reduce the concentration of these different pharmaceuticals by 90% for 1 million gallons per day of wastewater effluent. So a small town, a small city might have 1 million gallons per day of wastewater effluent that it treats, and you might need 10 hectares wetland to make that possible. And what I want you to take away from this figure is that this is the existing Prado wetlands, the area that's available. This is another set of wetlands, the easterly wetlands that were built in Orlando, Florida. So within a range of footprint sizes that are comparable to wetlands that people are already building to remove nitrate from wastewater, we were able to remove these pharmaceuticals from water. And the characteristic U-shape of the curve shows you that, as you might expect, the removal's better in summertime than it is in wintertime, because guess what? The sun shines more in the summertime. And so you can see here that this natural system was much more effective than the other systems that we had. And surprisingly to us, this managed natural system, this open wetland system, was also capable of removing waterborne pathogens. So this figure here shows you the footprint that you would be needed to remove the microbial indicators, E. coli and enterococci. And also it removed nitrate, which was a real surprise to us given that it wasn't the typical environment for denitrification to occur. And so this turned out to be a very favorable way to remove contaminants from wastewater effluent. And with the data that we had collected and the experiments that we did, we convinced the operators of the Prado wetland to build a demonstration scale wetland system. And so this is a picture that one of our friends took from the window of a Cessna. He's an amateur pilot. And it's the demonstration scale open water wetland that we built in the Prado wetland to replace the vegetated wetland that they had built before. And it uses our principle of using shallow water and blasting it with sunlight to remove the trace organic contaminants, to inactivate the waterborne pathogens, and to remove the nitrate. And we've been collecting monitoring data for the past year, and we've seen that this system's performing quite well at this large scale. And we've been automating our monitoring systems by using these solar-powered online sensors. So now I can sit at my desk and look at the concentrations of many of the things coming in and going out of the wetland and not have to go down there to make sure it's working. I told you that Los Angeles had used this idea of, wanted to use this idea of water recycling, but they also wanted to use this, another idea of groundwater recharge. And I think that this system here of advanced aquifer recharge is a good example of some of the technologies that geologists and microbiologists have taught us can be used for water recycling projects. So this is a project that was built in Aurora, Colorado on the South Platte River. And the South Platte River below the city of Denver is a lot like the Santa Ana River. It's mostly wastewater effluent. So the wastewater effluent from the city of Denver flows by the city of Aurora. And the city of Aurora is a rapidly growing city that doesn't have enough water. And they said, wouldn't it be great if we could drink the wastewater from Denver because we really need water? And this is the system they invented to make that water recycling possible. They do something here at the edge of the river called riverbank filtration. That is, they install a groundwater well adjacent to the river and they pump the water, and as the water pumps in from the river, it does the same thing that we saw with water 2.0. The microbes living on the sand particles remove contaminants. And then they take that water and they pump it to a second pond over here, and as the water percolates through that pond, more treatment happens with a different type of microbial community. And then they pump the water back out again over here at this recovery well, and they send it to a drinking water treatment plant. And that's the water recycling system that's used to convert Denver's wastewater to Aurora's drinking water supply. The other technology that's being used in Southern California is this idea of capturing urban runoff and using it as a drinking water supply. So I know here in the Midwest and in the Northeast and the Pacific Northwest, people worry about stormwater because it can cause combined sewer overflows. In Southern California, the city wants to capture that urban runoff, so the water that flows in the streets when it rains, but they don't want to put it in a rain garden or get rid of it for a little while and then release it to the sewer. They want to capture it and put it into the drinking water supply. And if you know anything about the hydrology of Southern California, it rains when it rains. It rains about 5 times a year, and it rains in massive storms. 4 or 5, 6, 7 inches of rain over a period of 2 or 3 days. And you're not going to use a rain barrel on the downspout of your house or a bioswale or a green roof to capture this water. You need to think big. And so this is one of the facilities that's been operating in Los Angeles County near Whittier for about 30 years, called the Montebello Forebay, where they capture rainwater runoff and infiltrate it into the groundwater supply. This is a project that's being built now by the city of Los Angeles in Burbank, where they bought an old gravel quarry that was abandoned, and they put a plastic liner in the bottom of it, and they're capturing all the rainwater that falls in the nearby neighborhood, and they're storing it, and then they're gradually passing it through this series of wetlands. And then in this figure, this area here is actually an infiltration gallery. So they're actually percolating that water to groundwater after it passes through the treatment wetlands. And that's kind of an interesting new project. I'm going to skip these slides here in the interest of time, and then just kind of end with a few remarks about how we make water revolutions happen. So I told you about some of the technologies that are being used as part of the fourth water revolution. And I think when you think about the water revolution that happens in wet places, or that's going to need to happen in wet places, you can see that, it's going to take some demonstration projects like the ones I talked about tonight, and it's going to take some motivation and some dedicated individuals to make it occur. I've been very influenced thinking about the way in which these new technologies will become adopted and become commonplace by people in an unlikely place. I've been interested in the way that the semiconductor industry thinks, and information technology thinks about technology diffusion. So this figure here is something that you can find like in an intro to business class that you might take before you go into the IT sector. It's called the S-curve for technology diffusion. And on the y-axis, it shows you the number of units of something that are actually sold or in use. And the x-axis is time. And so what you can see happens in the lifetime of a technology is first someone invents it, and then they develop a pilot or a prototype of it. And then they take that pilot or prototype and they show that it can work in a larger scale system. They make a demonstration of it. And then that demonstration convinces a group of people that are referred to as innovators, the kids who want to be the first one on the block to own it. They're going to buy it and build it. And then those innovators have this really cool new technology they're using, and then the other kids come over to their house to see it, and those kids are called the early adopters. And so those early adopters say, well, it works for that person, I want to buy one. And then the early adopters inspire more and more people to acquire the technology. We refer to them as the early majority and late majority. And then by the end of this S-curve, the only ones who don't have one are the laggards. So you all know how this works with a cell phone, right? A new cell phone comes out, some early adopters willing to pay an exorbitant amount of money to be the first kid on the block to have one, and then those tech geeks that you know go and buy them, and then you feel like, oh, I don't have one, I should probably get rid of my new old phone and get one, and the only person that doesn't have it is your grandfather, right? That's the idea of the S-curve for technology diffusion as applied to telecommunications. That occurs over a period of 3 to 5 years. So when you think about the timeline from an invention to getting something out on the market, it's very short. This is the timeline for wastewater technology. So a guy named Denny Parker did this analysis a few years ago, looking at the wastewater technologies that have made this transition up the technology diffusion S-curve. And the really sad thing about it is that for a wastewater treatment technology to make this journey up the S-curve is something like 30 to 40 years. And that's because the water infrastructure area is a place where there's low return on investments, there's a long lifetime of the infrastructure, and it's a field where we're really worried about potential adverse public health effects and consequences of building the wrong technology. And so we have to struggle. Like I told you at the beginning of the talk, we might only have 20 or 30 years to make this revolution happen, and we have a technology S-curve that takes 30 or 40 years to happen. And so one of the things we have to do is pay a lot of attention to the business system that takes new ideas and new technologies and brings them out to market. And so I told you a little tonight about our open water unit process wetland system. That was something that we invented about 7 years ago. We piloted about 5 years ago, and we did at the demonstration scale about a year ago. And so now we're in the process of looking around. We found our innovators. Our innovators were the Orange County Water District. Now we're looking for our early adopters, and we're actively seeking other utilities around the country that might want to build one of these systems to start that momentum up the technology diffusion S-curve. So some final thoughts from this side of the urban water revolution. I think I showed you tonight that the revolution is coming. I showed you some of the drivers for the revolution. I've even shown you the outlines of the blueprints of the revolution in urban water supply. And the key to making this fourth water revolution happen, whether it's the revolution in urban water supply or the revolution in water management, is advancing the next generation of technologies. I showed you kind of a pathway through which good ideas can be taken to the demonstration scale. But there was also something else I showed you. It was this idea of creating legitimacy or acceptance of new technologies from a skeptical public. I also tried to demonstrate to you tonight that this urban water revolution, unlike the revolutions that preceded it, is going to integrate the natural environment as part of the treatment system. Think about it. Water flowing out of our cities that was cleaner than the water that flowed into our cities. Think about it, using the ecological services of wetlands and aquifers and rivers and lakes as part of our treatment system rather than treating them as part of the disposal system. But before this revolution occurs, we have a lot of work ahead of us. And I think the revolution comes one way or another. It either comes through deliberate actions that we take as scientists and engineers and social scientists and politicians and community members, or it comes in a moment of crisis, like the crises that necessitated the building of New York City's water supply system, like the crisis that necessitated the construction of drinking water treatment plants, and like the crisis that led to the Clean Water Act and the construction of sewage treatment plants. So it's our choice. Do we want to have this happen deliberately, or do we want to happen in crisis mode? If we want it to happen before the crisis occurs, we need to invest and reinvest in science and technology research. You know, proportionally, adjusting for the effects of inflation, the amount of money that's spent on desalination research today is 1/10 of what was being spent during the Kennedy administration. During the Kennedy administration, we came up with the key technology that made seawater desalination possible. 40 years later, the reverse osmosis membrane that was invented by government-funded research became a viable product. Guess what? There's really nothing left in the pipeline, and there's a limited amount of money going in to create that next pipeline of water technology. We also have to foster this idea of technology diffusion. For too many years, university researchers and government scientists have been focused on novel stuff that could get graduate students papers and get them through their theses, and undergraduates too, by the way. You know, really, to think about technology diffusion is something new to me and new to many of my colleagues, and I think that this has to be introduced into the curriculum of people studying science and technology. And finally, as you might surmise from the projects that I've described to you, this is not something that occurs in your laboratory with a few graduate students. Some of these things that I showed you tonight took the cooperation of utilities and engineers and private companies to build. And in order to win their confidence and trust to spend the big bucks to build these things, you have to actively engage with them and be part of an outreach program. And that's why I spend a lot of my time traveling, not only to talk to groups at colleges and universities, but to talk to the people in the professional community, because they have to be aware of the importance of this stuff. So ending, I want to make some acknowledgments here before I end. Renew It, this stands for the National Science Foundation's Engineering Research Center on Reinventing the Nation's Urban Water Infrastructure. That's where we get a lot of the funding to do this research from, the U.S. National Science Foundation. And any of you who are undergraduates in the sciences, you should think about applying for National Science Foundation graduate research fellowships when you graduate. It'll make it easier to get into graduate school and make your graduate advisor happy. You can see a website for Renew It there. And Renew It is a collaboration between UC Berkeley and Stanford. And if you know anything about the Ohio State-Michigan rivalry, you can guess about the Berkeley-Stanford rivalry. So the fact that we can work together shows that when you have big problems to solve, you can put your differences aside. We also have collaborators at the Colorado School of Mines and New Mexico State University and the Swiss Federal Institute of Technology in Zurich. I put the logos there of some of the utilities that have worked with us, like Los Angeles Department of Water and Power, the Orange County Water District, and Discovery Bay, the little town that built our first open water wetlands. And I also put the cover of Water 4.0 in case you're interested in learning more about the history of urban water systems or the crises that they're currently suffering. I think there are some copies floating around here somewhere. You could probably borrow one from a friend. So with that, I'll end, and thank you again for your patience.
We do, even with the technological hiccups, and apologies for that, have time for a few questions.
Okay, so my question is, so you were talking about in the second water, I guess third too, but the second and third water revolutions, we were making sewage water into drinkable water? And are we like trying to do that again,
That's a good
just in a different way?
No, that's a good question. So the places like Lowell and Lawrence where people were getting sick from Lowell's upstream sewage, the wastewater, the untreated wastewater accounted for less than 1% of the overall flow. So the thing about waterborne pathogens, things like typhoid fever and cholera, is it takes a relatively small number of those bacteria to make a person sick. And so it was sewage contaminated water, but it was much less than 1% of the total flow. If you look at places like the Trinity River or the Santa Ana River or those water recycling projects, we're talking about the wastewater accounting for 50 or 100% of the overall flow. And so it's kind of a different degree of needing to purify the wastewater to make it drinkable.
You were discussing your open wetland systems as a purification process for the human hormones. They only work on a seasonal basis. Do you have any ideas of how you're going to lengthen that throughout the year?
Yeah, that's a good question. Certainly these wetlands exhibit this seasonal fluctuation, and wetlands that don't rely on sunlight, that rely on microbial processes, also will show a seasonal variation because microbes are less active at colder temperatures. Luckily for us in California, we have Mediterranean hydrology, and in the wintertime, when the wetlands aren't working very well, they're not being asked to work very hard because the Santa Ana River turns into a flood channel and most of the water bypasses the wetlands. So in Southern California and lots of places in the south and southeast and southwest, these systems would be less efficient in the wintertime, but in the wintertime you often have more dilution water. If you wanted to build these wetlands in the upper Midwest, for example, or in the Midwest, you would have to get creative, either to overbuild them, to build for that winter period, or to either not use them or supplement them with mechanical engineered systems during the off-season.
Have you studied how much the water evaporates when you start exposing all that extra water to the sun? How much are you losing of your water supply when you do that?
Yeah, so there are two ways in which you lose water in wetland systems, evaporation and evapotranspiration. So in the vegetated wetland systems, you have evapotranspiration, and you lose, let me kind of put it in context. In the wetlands that we studied in Southern California, you lose about 10% of the water over a period of 5 to 7 days. In the vegetated wetlands, we lose about 5% of the water in a period of about 3 days in the open water wetlands. So we're losing some water. It's not the water loss that we're most concerned about. We're worried about the increase in salt concentration because this is part of the desert Southwest and the water coming into the wetlands already pretty salty. And if it gets much saltier, it's going to start tasting funny and people won't want to drink it. So it's something we're always thinking about, and it's one of the downsides of both kinds of wetland systems.
I was wondering if you had done any research on the open water unit process cell in regards to chemicals that don't occur in sewage. I was thinking mainly toward the next lecture in hydraulic fracturing, if you think that possibly some of these chemicals could be removed.
Yeah, as part of our research program and this idea of technology diffusion, we're in the middle of a series of seminars with our students. And one of the things we're doing is we're looking at the market potential for these wetlands to be used for other applications. And so we've been examining the possibility of using these open water wetlands for removing herbicides and pesticides from either agricultural runoff and urban runoff. We've been looking at mining waste and waste from the oil industry. And we've been thinking about the water that's produced when you do reverse osmosis on sewage effluent, the so-called concentrate. We haven't been thinking about fracking water because we don't have a lot of fracking by us, but I would presume that these could be one technology that would be useful, provided that the concentrations of the organic chemicals were low enough and there weren't inorganic chemicals causing a problem, because obviously you can't break down many inorganic compounds, many metals can't be broken down.
Thank you so much for this talk. This was amazingly interesting, and I have a million questions, but I will ask just 3 if I can, just really quickly.
Can I choose which one I answer?
Yeah, absolutely, absolutely. I guess the first question, just as quickly, is how do you think we're going to pay for all of this? In part, I mean, there's all of the treatment aspects you've talked about today, but part of the urban water crisis is also an infrastructural one, just simply getting, if we have clean water, how do we get it to the different people?
Let me ask that one first.
Sure.
So, in terms of increasing people's bills, the public will accept a 5% increase in water bills. When you go much above 5%, they scream uncle, and people lose their jobs at the water utility. And that's unfortunate. I have a whole chapter in Water 4.0 talking about all the things we need to spend money on just to keep the water infrastructure that we already have operating. And so we might get there slowly by slow increases in water, but a recognition of the potential importance of the impending crisis seems to be the way we do it. So last week, California bucked the national trend. We elected a Democratic governor who didn't campaign. We passed a water infrastructure bond for $7.4 billion, which for about half of it is going to go to water recycling and urban water capture and reuse. And we passed a tax on sugary beverages in Berkeley. So you can see that not all of the country is hiding its head in the sand when it comes to water infrastructure. You can also see in Texas, where the state coffers are full based upon the windfall profits from oil exploration, they're spending a lot of money on water infrastructure because it's seen as something that could slow future development. So places that are rapidly growing and have cash to burn, Perth is another example of that, and places where people have recognition of the potential water crisis are going to raise money through bond funding and taxation. Second question?
Can I do that? One more? Okay. I guess what I'm curious about, if you could talk a little bit about how you see, you talked a lot about the kind of urban infrastructure, in some ways in isolation from the rest of the hydrological and kind of human systems, and in fact from the rest of the kind of natural systems. And I'm interested in how you see integration. I'm thinking particularly in the California case, integration with agricultural production, in the sense that most of our water use goes to agricultural production rather than for kind of daily life. And how does the model and the lines of the connectivity fit with the broader question where most of our water is going into agricultural purposes when the business demands for agriculture are very high?
Yeah, I grappled with that one for a long time. In the United States, 40% of our water goes to agriculture. About 40% goes to thermoelectric cooling for power plants, and 20% goes to cities. And in California, 80% of the water goes to agriculture and 20% goes to cities. The water issue in agriculture is, in my opinion, mainly a political and policy decision. We know that, for example, something like 80 to 90% of the almonds that are grown for export in the world are grown in California, and each almond takes a gallon of water to grow. I think the world could live with a few fewer almonds if it meant saving billions of dollars and saving California's cities from water problems or restoring endangered species. But we've been singing that song for 50 years now, and not much has changed. And so I took the perspective that I wanted to see what would happen if the people in cities tried to find their own path and not be held hostage to agricultural interests to solve their problems. If I was a benign dictator, I'd solve California's water problems tomorrow, and I'd come up here and I would solve your problems with pollution in Lake Erie, because I think a lot of that is a public policy decision and not a technology decision. But I'm not the dictator, and I'm not running for dictator. And so I think we're going to have to muddle through on our own, and that often means that cities are going to have to figure it out for themselves.
Thank you so much. Since you mentioned that, how would you solve our Lake Erie water pollution problems?
The way I understand it, there's this issue with non-point source pollution, And yesterday when I was at Ohio State giving a seminar, someone told me that something like, there are models that show something like 80% of the nutrient discharges are coming from something like 20% of the farms. And so it seems to me like we have the tools to put in riparian buffers, to change agricultural practices, and to grow something other than corn as a means of decreasing the phosphorus and nitrogen in runoff. So I don't claim that I could give you a plan tomorrow, but I think I'd start looking at agriculture, and in particular the farms that release the most nutrients, and I think we could do it without bankrupting the agriculture in the state.
Could you say just a little bit more about desalination? I'm curious whether there's, I mean, what are the barriers to it again?
There are none other than money.
Okay.
So let me tell you a couple things. There's a whole chapter in Water 4.0 about desalination, and it tells the story about how seawater desalination over the past 20 years has truly decreased its energy consumption to a point where it's now competitive with other forms of water provision. So in Los Angeles, for example, the amount of energy that it takes to pump water up and over the Tehachapi Mountains, that's kind of from the Central Valley into Los Angeles, is about the same as the energy required to desalinate seawater. And so if you're going to start over again in Los Angeles, you might decide that desalination was the way to go. So that's why Australia and Israel and Spain have decided that seawater desalination is the key to their future water supply. It's kind of a plug-and-play technology. It's not going to get much better, but it's pretty good now. That said, it's still about 3 times more expensive than these advanced water recycling treatment plants. So the utilities in Southern California are trying to do water recycling because it takes less energy to desalinate wastewater because it's less salty than seawater. The other thing happening in California is kind of interesting, and I describe it in the book. The seawater desalination plant that's being built now north of San Diego in Carlsbad, that is, they're in the process of constructing a 50 million gallon a day seawater desalination plant in Carlsbad. It's a public-private partnership, and it has a lot of people's feathers wrinkled because it's not being done by government. It's being done by a for-profit company, and a for-profit company that kind of messed up when they built their last seawater desalination plant in the U.S. in Tampa. They went bankrupt and the city was left holding the bag. The other thing going on is in California, there are a number of people worried about what happens when seawater desalination becomes a legitimate technology. Because if you've ever visited California and gone up and down the coast, you know that with the exception of the Los Angeles area and the San Francisco area, there's a lot of undeveloped coast. And that undeveloped coast is undeveloped because it used to belong to the military and it never had a water supply. The military's given it up, and now if you could stick seawater desalination plants up and down the California coast, there could be pressure from developers to open up that land to housing. And so there's this second kind of hidden agenda that people are using to fight seawater desalination in California, and California is the most likely place that the next seawater desalination plants would be built in North America. So the answer is we'll probably build them in Mexico and send the water up to the U.S. That fits with the theme, right, from last time, right? Okay. Oh.
With the microphone. Before I ask us to thank David Sedlak for this very informative talk, I want to remind you of 2 things. Sorry. First is the movie on Sunday. And second is if you want to continue to support the water charity work that we're doing with the SNC and encourage your friends to help reduce our bottled water footprint and have us in Ohio, a water-rich state, stop stealing his water by buying bottled water. Remember to the $5 charity donations for the reusable BPA-free plastic bottles that we've been selling to try to drink Ohio water instead of California water. So, thank you very much.